Hello, everyone. This is Mark Finney. I'm a research forester with the Missoula Fire Sciences Laboratory in Missoula, Montana. I lead a research team in fire behavior sciences, and we look at how fire spreads, the physical mechanisms responsible for that, using laboratory information as well as field collections. Today, I'm going to talk about wildland fire spread and discontinuous fuels. Now, the idea of discontinuous fuels is as old as the science itself, because it's pretty easy to recognize that even in the simplest fuel beds, such as pine needles, that the fuel bed is composed of discrete particles separated by gaps of air. And so even though we may generally refer to this fuel bed here, pine needles, as a continuous fuel, it's actually discontinuous, and under some conditions of moisture content and fire spread direction, for example, or wind, the fire may actually not spread in this bed because of the discontinuities. But today, what I'm going to talk about here is four different things. One, discontinuous fuel types, specifically they're obviously full of gaps between the fuel particles or clumps of fuel particles, different scale of discontinuities. We'll talk about some laboratory and field research on fire behavior and spread in these discontinuous types. Talk about physical processes in fire spread so we understand how fire is able to spread both in so-called continuous as well as discontinuous types. And then I'll talk a little bit about modeling and the needed field experiments for verifying how models behave and whether or not they're doing the right thing for these larger scale spread situations. So discontinuous fuels. Well, there's some fuel types that are obviously discontinuous, all the way from grasses to tree canopies. And in this case, we're talking about bunch grasses. These are perennial grasses, and they typically occur in bunches. And you can see this is a fescue, I believe. And there are gaps between each bunch in that photograph on the right. And this means that fire will not spread across that under some conditions of moisture, wind, depends on the orientation of the front, slope of the ground. Many of these factors determine the threshold when fire will spread and when it won't, and certainly how fast it does if it does spread. At larger scales, you can find clumpy fuels or discontinuous fuels in something like tussock grass. This is in New Zealand, and these tussocks are about 5 feet tall and getting very continuous now. You can barely see the gaps between them, and in younger stages after burning, they are shorter and the gaps are much larger. We see gaps all the time in shrub fuels. This is Cercocarpus montanus in Colorado at the lowest elevations in the ponderosa pine zone. This you can see has a clumpy structure to it, lots of gaps in the shrub canopy, but they're filled in by various kinds of herbaceous fuels and grasses. We often think of kind of the classic clumpy fuel type or discontinuous fuel type or desert rangelands, desert shrublands. This is big sagebrush, and you can see in there that there's wide separation between a number of these sagebrush plants. Individual plants are easily identified. There's bare ground in between them. There's bunch grasses and probably some other herbaceous or forby type fuels. Now, the thing about big sagebrush, it grows at different sizes. Some are big and some are smaller. This is much taller, big sage, and you can still see the clumpy, gappy structure in this. And what it means is that fire spread is going to exhibit thresholds. Under many conditions of low wind or high moisture or shallow slopes, you're not going to be able to get fire to spread at all. But when it does spread, it's going to spread very fast. The same way in pinyon juniper forests. This is pinyon juniper, and you can see the wide gaps between these tree canopies, almost nothing in between, a little bit of grass on the ground. This is a close-up underneath the canopy here, but a little bit of litter, some dead and down material, but and a little bit of sage in there too, but a lot of bare ground. Prickly pear cactus. So here's just a look at some of the litter. Okay, but one of the primary problems facing the interior West is the invasion of annual grasses, in this case cheatgrass, Bromus tectorum. And the thing about cheatgrass is that it's an annual grass. It germinates from seed every single year, so it matures very early in the spring, dries out, and is a very continuous cover. And therefore, it fills in the gaps between what would ordinarily be a very discontinuous type with these sagebrush plants. And so it can burn every year very frequently. And of course, being very fine fuel like that, it can spread very fast, making it difficult to control. We'll talk more about that in just a little bit. So let's talk now about fire behavior and spread in general in these discontinuous types from field and laboratory research. So here's an article published in 1981 by Carlton Britton et al. Will your sagebrush range burn? Okay, and so they noted with prescribed burning that it was difficult to predict when you would actually get fire to carry. And you can see a picture in the lower left of them lighting a line of fire. So the main variables that they found in their investigation, in addition to the wind and the moisture, is the two factors. Look at the graph on the right: sagebrush canopy cover from 10 to 50%, and then the herbaceous fuel loading in pounds per acre, and that's to fill in the gaps, right? So on the left of that curve, it won't spread. At very low canopy cover, you need a very high, I actually can write on this, you need a very high loading of herbaceous material in order to get it to spread. At very high canopy cover, you can get away with low loadings of herbaceous fuel because the continuity is there. Okay, now one of the difficulties with canopy cover as a measure of continuity is illustrated by this slide here, where for the same degree of cover, in this case 50% cover, and you can see three different panels there of blue dots showing different size clumps. You can think of that as a plant. The cover, the individual canopies of those plants, it combined 50% cover. And at 50% cover for very small diameter plants, the spacing between these plants is very small. So look at the graph down below. I'm circling it right now. For a given cover fraction, in this case 10% to 50%, if you have a circle diameter of 1, which is just the smallest one I'm showing here, there's the gap distance between small plants is also small. But look at it to the far right here. For big canopies, large canopies at the same cover, say 5 times the diameter, here you're talking about a much wider gap distance for the same cover, total cover. So cover is a very poor variable to use in trying to describe continuity, because it's really about the gaps. The gaps are what determine the amount of heat transfer necessary to cross those gaps and ignite fuels on the other side if you're talking about fire spread. Okay, so these are random arrangements. Obviously, if it was different, if it was a regular arrangement of plant canopies, or if it was, say really clumpy, they were all clustered in certain areas, these relationships would be different. But cover is a poor representative variable for continuity. Let's look at a paper on spread thresholds in mesquite shrublands in Texas. This is by McPherson and Henry Wright. And in this case, they found 3 important variables to predicting when their prescribed fires would spread under a particular set of weather conditions. One is the wind speed, where obviously the higher the wind, the easier it is to spread. That's on the y-axis. The x-axis is the surface stem moisture content, and this is for the grasses. And the so from 3 to 8%. And then there's 3 different lines that represent the stem diameter of the mesquite shrubs. And this is a proxy. It's an allometry for the canopy dimensions. So bigger diameter, stem diameter, means a bigger plant. Okay, and so look at these lines. Everything to the left of the line means it will spread. Okay, and so the bigger the plant canopy, in this case, in their study, meant that there's more area to the left of this 18 centimeter line than there is to the right. It means it's more likely to spread. And so on a 6 centimeter diameter mesquite shrub, what you're seeing here, because the canopy cover, I guess, is a lot less, that there's a lot less area to the left, meaning it less likely to spread for a given moisture content and wind speed. Another prime example is the spinifex vegetation of Australia. And this is in the deserty areas covering a vast expanse of Australia. Spinifex is a certain species of a bristly shrub, spiny shrub, and it looks like there's some grass in here, but look at all the bare ground in between. So this clearly exhibits thresholds in spread because of continuity. Now, one study of this, there's been many, this is by Neil Burrows et al. In 2006. What they did is they found empirical relations to predict fire spread rate on the y-axis. Okay, the fire would spread faster or slower based on wind and moisture and loading and things like that. But I want to point out primarily or emphasize the x-axis, the spread index they called it. This was the likelihood of fire being able to spread at all. And that is a function of wind, a positive function of wind, positive function of loading, and a negative effect of moisture content, very similar to the other studies, okay? And so any positive value for the spread index, anything above 0, okay, anything above 0, they said the fire would spread. Okay, well, obviously their other equation for spread rate shows some negative values. And so you can't have negative spread rate. And so fire will only spread in this upper right quadrant here, and that is when the spread index is greater than 0, when the wind is high, when the loading is high, and when the moisture is low, okay, then the fire will spread, and it will spread very fast. So this is an example of empirical studies, an empirical study dealing with these discontinuous fuels. And when you look at Google Earth out in these spinifex shrublands in Australia, what you see is very strange fire patterns, burn scar patterns. These are very angular, very sharp edges to them, very jagged. And the reason is because the fire cannot spread in the flanking direction. If it's wind driven, it will not expand laterally. It will only spread in the heading direction. And as the wind dies or it encounters sparser fuel types, you end up getting these very narrow fingers that eventually just wedge out to a nice point. So you get these very jagged and strange patterns driven by the wind because it's limited. The discontinuity limits the spread potential in the lateral direction. Another study, not going to spend too much time on it, but it does make an important point here, is the size of the ignition. In discontinuous fuels, it's much harder to get a spreading fire if you have a point ignition, or spot ignition, as they're saying here, or a very narrow line. Okay, and it's much more likely to have a line ignition, a wide line ignition, be able to spread. So this is spread rate on the y-axis and canopy moisture content on the x-axis. This is in heathlands. It's heather in the UK, and the filled circles are spot ignitions that were successful. The open circles are spot ignitions that were not successful as the moisture content got larger. But only line ignitions, wider line ignitions, were able to spread at the highest moisture content that they found. Very, very typical of discontinuous fuel. So let's talk about fuel continuity at a different scale, not at the individual plant or particle scale. Let's talk about it at a landscape scale. This is a graphic from some work that I did about 20 years ago. We're looking at the effect of different spatial fuel patterns on a broader landscape scale. So look at panel A, you're seeing two ignitions showing an elliptical fire growth pattern, and the red indicates the intensity and the spread rate. So it's a constant fuel type. And so you see the higher intensities at the head of the fire and lower intensities. So the head of the fire here, lower intensities at the rear. Okay, but the fire spreads from here to here in the amount of simulation time. Now, if you change the fuels, if you add a second fuel type that's burning slower, and you have these same two ignitions, what happens is the fire spreads slower. It's forced to spread across these slow types, spending time that otherwise would be speeding ahead. Okay, and so you get a very efficient reduction in the forward spread rate by having parallel strips. That's assuming that you know which way the wind's coming, right? Well, these bottom two panels are variations on this strip idea. Is what if you have a discontinuous pattern, right? In C, it's a parallel strips. In D, it's more of a herringbone pattern. But this just shows you that the fire growth can be retarded by having certain spatial patterns that are very effective and much more effective than random. If we just threw a dart at the map and achieve the same overall cover of that second blue fuel type, we wouldn't have nearly the effect on fire growth. Now, this whole theory here was tested by a fellow named Gil Dustin. He's fire management officer with the Bureau of Land Management, still to this day, I believe. I'm not sure what his position is, but this is an actual field test in the Skull Valley of Utah, southwest of Salt Lake City. And you'll see right in the center there of the page, you'll see these 1 square mile sections where he actually implemented these spatial patterns with a bulldozer and a disc unit. Okay, at different, he called them vertical gaps, but it's the separation between the rows, okay, with some very narrow, 50 feet and all the way up to 500 feet. So it's kind of hard to visualize this. So these are all pictures from Dustin's work. And so there was a bulldozer with this chopper and this disker, and then they seeded it with perennial grasses. I can't remember the species, but attempting to type convert it to something that was more discontinuous and would stay greener longer into the summer. And so these are aerial photos of the actual disc line pattern. You can see on a very broad scale, there's 1 square mile across there. Close up of that. And here's the contrast between a very dense pattern of these disc lines and then a more open pattern. And here's what he found. They put in these patterns and then they waited a couple of years and then they lit them on fire under pretty extreme conditions where the fire ordinarily would present great difficulty to control forces. And so what happens is as the fire starts spreading between these patterns, it has to dodge and weave around, kind of like a pinball in a pinball machine. It's bouncing off the bumpers and not making progress in the forward direction because it's having to do a lot of lateral movement. And so what they found on the right-hand side summarizes what they found. Without disc lines, the fire spread at a rate of 540 chains per hour, which is very fast and very difficult to control such a fast-moving fire. But with only a 500-foot distance between these lines, a very, very low density of treatment, what they found was that the fire spread rate was cut in greater than half, making it far easier to control. So this is a dramatic example, probably the best example I know of really trying to change fire growth on a landscape basis with a strategic pattern treatments. Let's talk about laboratory research on fuel discontinuities. This is inside our burn chamber at the Missoula facility. We're burning Excelsior here, wound around 4-foot tall spindles, but we actually did 1 foot and 2 foot and 4 foot tall spindles at different spacings without wind, but on an incline. And we were looking at the effect of fuel discontinuity in the longitudinal direction, with the direction of spread, on how fire spread and how it was stopped. So what we see here, this is a close-up view of one of these on a flat ground, is that these fuel rods, once they start to burn, these spindles full of Excelsior, once they start to burn, the flame envelope increases in width as it goes up, and it is igniting each row at the top that then spreads down. So it ignites up here, and then it spreads down, increasing the width of the flame profile, which allows it to spread across the next gap. I'll show you an animation or a couple of schematics here in just a minute. But what we see here also is something called a combustion interface that's inclined. You notice that this angle here off the horizontal it's inclined, and it's also kind of curved. Let's explain that. So if you take some video over some period of time, some fairly short period of time, in this case 8 seconds, this is thermal IR video. What we end up getting is a probability map of flame presence. So instead of just having this flame or no flame, we actually, because the flames are moving, they're flickering, we're getting this probability of flame being present. And this forms this nice curved combustion interface between the burning fuel and the unburned fuel. So if you took a time series at each one of these dots, you see these dots in the upper part of the screen, across this ignition interface here, what you would be able to see is the time series of flame contacts. Right? Flame is flickering, it's moving back and forth, and it's not always there. So this pixel location that's in the deep red here, that's this first box right here. And what you're seeing in these dark blue areas, this is area where the flame is present. And the light blue areas, the flame is not present. It's just ambient air. So most of that time, this is 8 seconds of time, the first frame to the last frame over 8 seconds, shows that most of the time the flame is present there, only a few periods of ambient air. But as you move farther away from the continuous flame, what you see is that the frequency of the flame presence becomes less and less. It is far more intermittent the farther you go away from the flame. It's still there. There's still a few flamelets that making those long excursions away from the front, and those are what's actually contacting fuels out ahead of the fire. So the way this kind of works is, if let's say that we ignite one of these spindles at the very top and top of the fuel bed, what happens is you see that the flame envelope expands with height, both due to entrainment of cold air, but also the adding of fuel gas, fuel mass with height. And as this flame spreads down the spindle, the flame volume, the profile of it expands, and if it expands enough to where some of those flames are able to contact the next row, then you get an ignition. And so what we're seeing here is downward spread of the flame, the expansion of the flame profile, and you get contact, literally just intermittent flame contact with the adjacent row, and it ignites there. And then that one spreads down the spindle and until it gets wide enough to cross, right? And then you get an ignition at the top. So we get downward spread, but we get upward acceleration of the flames due to buoyancy, and they contact the adjacent fuel elements. And if you continue this sequence, what you start to get is a series of these ignition events, and you get this curved combustion interface, right? So that's very similar to what we saw from the video and from the images, thermal image before, this curved combustion interface. So what does this mean for fire spread in fuels on steep slopes and with different fuel depths? Well, shallow fuels, because you have such a limited downward latitude or extent to spread, means that you can only develop flames a certain height, right? This is without wind. And it may be that in short fuels, such as mown grass, you do not have enough vertical height in order to generate flames tall enough to cross the gaps. Contrast that with very deep flame zones, where now you can actually establish a much more vertical burning and a wider flame profile, because you're burning a lot more fuel per unit area and unit time. And then you can cross the gap. Slope, a steeper slope, means that you're more likely to intercept the uphill fuels, are more likely to intercept this expanding flame volume, and therefore fire will spread on steep slopes independent of all the other factors easier than it will on shallow slopes. This is independent of wind. Obviously, wind has an effect, and other factors too. But just due to the widening flame profile and the taller fuels and steeper slopes, fires will spread. Okay, so that's a summary of some of the research on fire behavior and spread in discontinuous types. Let's talk about physical processes in fire spread. So wildland fire spread is what's called a coupled system. We have three main pieces of it. One is the combustion and energy release at the top. When something burns, it releases energy. Some of that energy is heat, and some of that heat is then transferred to fuel particles ahead of the fire, just like we've seen. And if those are heated sufficiently at sufficient rate to overcome cooling, natural cooling, then the ignition takes place. As those start to burn, they release energy, and the entire circle of life continues for fire. This is called a coupled system because there's no good place to start the whole thing, right? You have an external ignition source that comes in, such as a match or a lightning strike, but then the entire system is self-sustaining. And what goes around comes around. So it's not easy to distinguish what is actually causing the fire to spread. Is it enhanced heat transfer? Is it something to do with the fuels and the energy release? Is it something about ignition? They're all related in this coupled system. So all of these factors are also affected by the environment. We're familiar in fire behavior with the fire behavior triangle, right? Fuels, weather, and topography. Certainly all those factors play in this system, right? Weather and the wind and the variability in those factors, the topography, as we've talked about already, fuel properties, like the moisture and the continuity, of course, that's what this talk is about, all play into this in a very complex way because they're all related. Everything is related to everything. And to make it even more coupled and more interconnected, the fire itself makes a difference. So you can have identical weather, topography, and fuel properties, yet the fire, when it's narrow, won't spread, but the fire, when it's wide, will spread. If it's strongly curved, if it's very, very pointed, it may not spread. If it's very wide and flat, it may spread. So, plus if it's oriented to the flank versus the head, it may not spread. All of these factors, the fire itself determines how the fire spreads. That's what a coupled system is. Okay, so I mean, that's why we're still in business studying fire behavior, because it's not just a linear system. It is a tightly coupled, nonlinear, dynamical system. Okay, so let's talk once again quickly about wildland fuels. A couple of really obvious things I want to point out to you that have profound implications for how fires behave, wildland fires, as compared to, say, industrial fires or those in built environment, such as a structure, a house, burning. In wildland fuels, we have fine fuels, primarily leaves and needles and twigs and grasses, fine material, a millimeter or so in diameter, maybe a little bigger. They're discrete particles, right, separated by gaps of air. Simple statement, but very profound for fire behavior. These gaps of air mean that somehow the heat has to go from what's burning across the gap to receptive fuel to ignite it, and it has to do it at a rate that's sustainable for the fire. We also have live vegetation, right? This is very different from industrial fires of fuel spills or house fires or apartment fires, right? Most of that fuel is dead. It's large material and it is not living. I mean, yeah, and not living in it. So let's look at in detail here. It's the combustion and energy release part of this process. So combustion energy release. Well, this here is a diagram of a fire spreading from left to right. And you're seeing the flame extension above the fuel bed. On the far left, you're seeing those black dots within these cells. Those cells are some arbitrary spatial discretization of the fuel profile. And the black dots, the black color, indicates they're already burned. All the fuel is consumed. The red dots all indicate they're actively burning. The pyrolysis is taking place. The gaseous component of these solid fuels is being released, and it's being merged into a flame zone that is releasing a great deal of energy. Now, on the far right is fuel, virgin fuel that is yet to be heated, yet to be pyrolyzed, yet to change from its ambient state. In the middle is this fuel heating area, where the heat from the burning fire is being transferred ahead by radiation and convection. And there's some gaps put in there just for illustration, but the fuels are heating. They're no longer in their ambient state, and they are beginning to decompose as they get closer and drying out as they get closer to the fire. So the fire is advancing from left to right. Now the combustion energy release here is within the burning zone. We're just talking about flaming combustion now, not glowing combustion after the fronts pass by. Is a function of all these factors. The fuel particle sizes, the loading, the fuel bed depth, the packing, that is how densely it's compressed, and the moisture content, and a whole number of other things. There's different ways to describe this. One is the burning rate, the mass per unit time per unit area that is burning in the zone. And that's an important way to look at this, an important metric. But a simpler way to think about it, just for fine fuels and for just for the flaming phase, is the flame residence time, right? So this is the total amount of time that flaming persists at a given place. So pick a cell here. As soon as it's ignited, the clock starts, and when the fire passes to the end and flaming is no longer visible, that is the flame residence time. The flame residence time is, it's abbreviated T sub r, and it's in seconds. T sub r is a function of the flame zone depth and the spread rate. Okay, so if a fire is spreading very quickly, but it doesn't have very long residence time, it might have a very narrow flame zone. Okay, on another way to look at it, if fire is spreading very slowly, but the residence time is very long, then the flame zone depth can also be very long. So flame residence time is equal to the depth of the flame zone divided by the spread rate, and that gives you seconds. So how do we know what factors affect the residence time and the burning rate? Well, we do a lot of experiments. This is some cardboard fuel particles in our laboratory, and what we're seeing here are fuel beds composed of these different cardboard fuel particles. We design these on the computer and we print them out on a laser cutter. So we use cardboard. We also use MDF, which is medium density fiberboard, and we can engineer any kind of fuel bed we want with big particles and low packing, or short particles or deep particles, any packing particle, fuel particle or fuel bed level factors, and we can put them in the wind tunnel or on steep slopes, and we can see how they burn. So let me give you an example of how that looks. So this is a small version, just a demo bed that we use often, but what you can see looking down from above, this fire spreading from right to left now, you can see that the tines of this, in this case it's MDF, these tines are burning, and there's a very well-defined bowed flame zone here, right? This is all the glowing combustion after the fire, but at the beginning, or at the head, what you're seeing is all of this area that where individual fuel particles are contributing their pyrrolysate to the overall flame zone. And you can see the individual flamelets that all merge into a single flame zone. Kind of interesting. And in a bed like this, you can easily determine from the ignition point back to the point when it goes out, right, the flame zone depth and residence time. So this would be flame zone depth. And then, of course, there's the residence time here. So that's an experimental way to do this. Let me show you some of the things that we find when doing this. If you keep all the particles within a fairly narrow range of size classes, what you find out that is that, and they're all primarily fine fuels, okay, very much like leaves or needles, that size class. What you find out is that the residence time is almost entirely a function of the packing ratio. The flame residence time here is a function of beta, is the packing ratio. That is the fraction of the fuel bed filled with fuel, right? And you can change beta for a given particle size. Say you have a bunch of toothpicks and you compress them all into a shallow block and burn that. That has a high packing ratio. But if you fluff all these toothpicks up and stand them on end, then that's a very low packing ratio, low volume filled with the fuel particles. What you see here is 92% of the variation in these cardboard fuel beds is a function of only beta. Only the packing ratio determines it. So for a given particle size, you could have a residence time as low as 7 or 8 seconds and as high as 70 seconds, simply by changing the packing. Very interesting. Now we can improve upon this relationship by adding some other factors. So on the right-hand side here, you see the residence time is a function of beta, okay, but it's also a function of sigma. Sigma is the surface area to volume ratio, where very small particles have a high surface area to volume ratio, very large particles have a low one. But here it's inversely related to sigma, so but a positive function. So bigger particles burn longer, denser beds burn longer, and higher loadings burn longer. So W is the mass per unit area. So we have residence time as a function of the packing ratio, the surface area to volume ratio, and the loading, all of them positively related. And here we still only get 96% R squared for all of this, okay? But it allows us to predict the residence time for a single size class of fuel, fine fuel, based on the particle and bed level properties. So the fuels are very important here in determining the energy release rate or the flame residence time. So another aspect of combustion energy release here is how much energy is released in the flame zone, not just the residence time, but the fire line intensity. Now this is abbreviated I sub B for Byram's intensity, named after George Byram. He was a pioneering fire scientists in the 50s and 60s, even into the 70s. But anyway, this is in kilowatts per meter, and so this it's composed of the contribution of energy release from all of the particles within the flame zone depth. And here's the equation. The I sub B, so fire line intensity, equals the heat yield, the heat content, the low heat content of the fuel, times the mass per unit area, the weight of the fuel, times the spread rate. Now, fire line intensity is related to flame length. There's lots of different empirical relations here, so I just put I sub B is proportional to flame length to some power. So the bigger the flames, the more intensity. Now we can't see intensity, and so flame length is a great proxy for intensity. Big flames mean high energy release rate from the total flaming front. So we know about combustion and energy release in flaming. Let's talk about the other parts of the circle of life for fire. So one is the heat transfer and how that influences ignition. I'm going to talk about both of these kind of together here. You could separate them out if we had more time, but let's talk about the heat transfer from what's burning to these particles that are leading to ignition. How does that happen? So here's our diagram again. We have radiation is one of the modes of heat transfer. This is thermal radiation, and you're seeing radiation from the flames here, but also radiation from within the bed forward, heating other particles. And so there's two sources: bed level radiation from all the solid fuel radiating. It's very, very efficient because it's solid material. Here, these are hot gases and very small soot particles. And so even though the gas temperature is high, there's very low emissivity generally in flames until they get fairly deep, 2 or 3 meters. But you still get radiation from the flames that's heating the surface of the fuel bed. And so this thermal radiation depends on the flame size, the width of the flame zone, the duration of the burning, that kind of thing. Now, what I want to show you here is two different particles. Let's just stop this for a minute. This particle on the left is a 12 millimeter particle. It's 12 millimeters in diameter, about ½ an inch. Okay, and the particle on the right is a 1 millimeter particle. And these are being exposed to a radiant panel, and they're only about 7 centimeters or so away from the surface of that panel. And this panel is radiating at about 40 kilowatts per square meter. So about 40 times the solar flux, radiant flux received on your skin from the sun on the sunniest, hottest day, about 40 times that. If you put your hand where those particles are, you would burn you in a second. So very, very hot. Maybe this is a radiant flux equivalent to about having, maybe a meter tall flames, maybe a little bit larger. So I'm going to continue this, and you think about which one of these particles will ignite first under a constant radiant flux, the big particle or the fine particle. So as we watch, this is sped up, obviously, because we don't want to spend all our time watching this video over and over, but the one on the left is ignitable in about 30 seconds. So it'll start smoking, you'll start seeing pyrolysates come off of it, and those pyrolysates are flammable, and they can be ignited with a pilot light. The one on the right, the small particle, will never ignite, ever. We could leave it there all day and all night. It would not even pyrolyze. It won't decompose. It won't start producing smoke at all because it is so efficiently cooled, bathed in the cold air. Fine particles are like cooling fins, just like on your engine or on your CPU in your computer, and they are much more efficient at exchanging convective heat with the cold air around it than large, thick particles. And so if you have a thermocouple that's sitting on the surface of the thick particle here in red and the thin particle in blue, you can see their different response to exposure to radiation. This is a time history. So on the x-axis is the time after exposure at about 5 seconds. What you see is the temperature, both of them begin to rise. But the thick particle increases its temperature and keeps on increasing well above the ignition point where it finally ignites after about 26 seconds. Looks like 30 some seconds to me. But anyway, and then it keeps increasing as it starts to burn. But look at the blue particle, the 1 millimeter particle. It just gets up less than 200 degrees and just bounces around. That's pretty interesting. And the reason is that it's still heating from the radiation. This is heating, but it's also losing heat as fast as it gains it. And so it can never heat up. It's losing it to the surrounding air, whereas the large particle cannot do that. Okay, so let's have a look at another fuel property that affects how radiant heat transfer and convective cooling. In this case, what we've got is a ball of Excelsior. This is the same woody shreds that we were using for these spindles in the discontinuous fuel experiments. On the left-hand side, these are compressed. With my hand, it's the same amount, same moisture content. Everything's the same distance from the burner. But on the left, it's compressed into the tightest ball I could make it. And on the right-hand side, it's very, very loose. And so watch what happens. The one on the left, after about 20 seconds, starts pyrolyzing flammable vapors, and it auto-ignites. Okay. The one on the right will never ignite. It will never even begin to pyrolyze or decompose or char, nothing. It will sit there all day and all night, and nothing will happen because it's cooling. Those particles are surrounded by cold air that is constantly exchanged as the surface of the particle heats up. The warm air then in contact with that particle rises and is replaced by cool air from the surrounding area. Now, that's natural convection. That is not forced convection. If you were to blow cold air on this, you could even increase the convective cooling even more. It's much more efficient, but we don't have time to get into that. Okay, so it's just another example. Here's just a picture. This is not a video. This is some grass basking in the glow of a 41 kilowatt per square meter radiant flux. So very hot. None of us could put our hand in front of that to move that sample in there. We needed gloves for sure. Anyway, this is the problem with radiant heat transfer in fires. It's usually insufficient to heat up fine particles in the cold ambient air. So that brings up convection. How then is the heat being transferred? If radiation is insufficient for fine particles to heat up, pyrolyze, and ignite, then convection has to be it's the sole remaining heat transfer mechanism, right, across these gaps. And a couple characteristics I want to talk about next. One is the intermittency of the flames. So the flames, just like watching a campfire, they flicker and they dance and they move, right? And so we're going to see examples of this kind of movement. The flames are not constant. They don't provide a constant source of convective heat transfer. The other is vorticity. That's just the spinning of the air. And we see a lot of vorticity in fires, and I'll show you where that comes from. So watch this for a moment. This is a view of one of our cardboard burns spreading towards us. It's spreading towards us. And what we're seeing is a couple of things that you've already picked up on. The flame sheet is not just a continuous big glowing rectangle. It's divided into peaks and troughs, right? You have some places where the flames are a lot taller and some places in the middle where they're not so tall, where it actually looks like the flames are going down and going forward. Well, that is very important. Here we have peaks on 1, 2, 3 peaks, right? And we in the middle between those are troughs. The way these are created is by the simplest way to explain it is that these very hot gases, they're about 1,000 degrees Celsius, and they're very low density, kind of like a hot air balloon, but much, much less dense than that. And so they want to rise. They're created down next to the ground, and they want to rise. Well, they can't pull air in from underground to replace that air, right? They have to pull the air in from above. So if a parcel is rising in one place on the left, then a parcel of air is descending next to it in order to replace that air. And this creates a spinning motion of the flames, vorticity. So we have rising air on the left. Yeah, I'll draw an arrow, rising air here, descending air here, rising, descending. So when you watch this, you notice probably that we're seeing a lot of what's called forward bursting down in these troughs. As this cold air is descending, forcing the flames down into the fuel, it splashes them forward from the fire. And without this kind of action, you really wouldn't get these fires to spread at all. So it's this process of buoyant upward acceleration of the flames and downward replacement air forcing the flames down into the fuel. Okay, so this is what it looks like. You end up getting these pairs of vortices. And so sometimes they're called streamwise because they're moving with the stream. Streamwise vortex pairs. And where two of these converge in the down direction, okay, I'll just draw an arrow down direction, this is where the flames are being forced down and forward into the fuel bed, where a lot of the convective heat transfer is taking place. Where these vortices converge in the alternating upward direction, right here, that's where the flame is pushed up into a peak. So you down, up pattern. And we see this in every fire. Doesn't matter how big or how small the fire is, we see this peak and trough pattern at the front. And now you know how it's caused. And you know what it causes. It causes the fire to spread by convective heat transfer. So this intermittency, another characteristic of convective heat transfer is intermittency. And so the flames are highly fluctuating, right? And they're extending forward and then withdrawing and extending forward from the edge of the flame zone. Well, what causes that? Well, look at this video, and what you're seeing looking down on the fire as it's spreading up towards the top of the screen is you're seeing these convex parcels. They look like they're little dish-shaped parcels. And what these are is these are toroidal circulations. All that means is like a donut, where it's the circulation, see in the upper left-hand corner, what you're seeing is this donut of circulation where it's going down in the middle and up around the outside of the donut. Okay, down in the middle and up around the outside of the donut. And these parcels are kind of coherent motions in the flame zone, they're called. They originate near the rear, even before the flame shows them to us. And they advect, they move coherently, merging sometimes with other ones adjacent to them, and then they move downstream. And when they reach the leading edge of the flame zone, what happens to them is they kind of splash forward and splash their flames on the edges into the fire ahead. They move from the start in the back, and they move to the front. Okay, downflow in the middle. So this is this downdraft that you're seeing caused by the replacement air, all this rising hot gas. Now, watch here. This is a video. This is a video of an experimental fire that one of many that we've done in New Zealand with our partners over there. And this is in crop stubble. It's about a foot tall, 0.3 of a meter or so. And what we're able to generate with a pretty strong wind, about a 5 meter per second, 6 meter per second wind, is a 5 meter flames. Pretty darn tall. You can see us walking around down there, little ants. But what I want to point out here, I'm going to stop this. I want to point out these circulations, these toroidal circulations, these coherent parcels behind the front. Okay, watch again as we restart this, and also look at the peak and trough structure of the flame zone. Right, you're seeing these peaks and troughs. You see these parcels that they're clearly a downwash, and the whole parcel moves its way forward. This is just an image. This is just an image of the fire coming at us. You can see our instrumentation in here to capture various characteristics of the fire. But the peak and trough structure, you can't really see it because the flames are meandering laterally so fast. But if you slow it down, you can really see it. You can also see the flame residence time. The flame only lasts at a given point on the ground here for about 10 seconds, and that's it, and it moves on. This is another video. This is in gorse. This gorse is about 1.5 meters tall, more or less. And you can see the patchy structure of it. Now we're starting to talk about discontinuous fuels, right? The green material here is the gorse, and in between it is grasses, primarily. And there's some bare ground and some game trails through there, too. So this is in New Zealand about a year ago. Now, this 1.5 meter tall material, fuel type, produces very, very tall flames, about 15 meters. I want to point out something on the left-hand side that shows you. These are trucks parked there, pickup trucks. And so as this fire progresses, realize that these are very, very deep and tall flames, about 50 feet tall. And what's interesting, take a look inside the flame zone itself. You'll start to see these downwash patterns, these downbursts of air replacing the hot flames, and they're pushing kind of like a cat's paw on a field of grass, pushing the flames out from these from the center. Okay, those are those coherent motions. And so even with very, very tall flames, you're seeing the same thing as we see in the laboratory. Due to buoyancy and the replacement air, the exchange of hot buoyant parcels and interactions with the colder atmosphere coming down. So all this intermittency and this high variability, what does this effect have on fuel particles? How do they respond to it? Well, one of my colleagues, Jack Cohen, instrumented a number of our burns in our cardboard. You can see the cardboard tines there. And this is a radiometer right here, okay, which measured in the radiant flux. These are the 12 millimeter particle and the 1 millimeter particle, and they've got a thermocouple embedded on each one, and a pair, another thermocouple right next to it in the air to measure the gas temperature impinging on the particle. Okay, so this is a time series showing the history of what happens to these instrumented particles. We're just the fine one. We're not even dealing with the thick one in this. But so we have time on the x-axis. On the y-axis, we have irradiance. Over here, irradiance in kilowatts per square meter. So you remember our radiant panel was about 40 kilowatts per square meter. This maxes out at about 30. So this is a spreading fire approaching our fuel particles. Now the red is the irradiance. Okay, so the irradiance rises fairly smoothly. There's some jaggedness, but it rises fairly smoothly and predictably, with ignition taking place at time 140 seconds after ignition. Well, the blue line is the air temperature, or the gas temperature that's whisking by the particle, and the black is the particle surface temperature. So let's zoom up on the last 20 seconds of this particle's life, and you'll see these blue spikes, right? So these are these forward bursts of flame pushing forward from the leading edge of the fire, enveloping the fuel particle. And look what happens to the fuel particle. In this area, the surface temperature of the fuel particle increases. And then when the pulse of hot gas goes away, replaced by ambient air, what you're seeing is the decrease, the slow cooling of that particle until the next burst hits. Then there's a stair step up and a slow cooling. And every time there's a contact with a hot particle, you get a stair step up until it finally ignites. Now, what's interesting is the particle is cooling even though the radiation is ascending the whole time. Radiant flux is ascending, and yet the particle is cooling. This is a realization of this convective cooling that we've already seen. So the fuel particles are heating up in a stair-step fashion. They're taking the stairs and not taking the escalator. It's not a smooth transition to ignition. Last subject is modeling and the needed field experiments. So for modeling, there's many different ways to include these kinds of physical processes in a model. You can have very simple models like we're talking about here, or you can have some very, very complex and sophisticated models. They're all actually sophisticated because they include the physical processes in a coupled nonlinear dynamical system. But let's talk about a simple model here. It's a one-dimensional model. It just in a straight line away from the fire edge. We're talking about the heat transfer, the combustion, and the ignition taking place just along this line of cells, just like this diagram here in the lower right-hand corner. So in this simple physical model, we have the combustion processes represented very simply through a flame residence time equation. We have the heat transfer from radiation and the convection ahead, and we have, of course, ignition behavior of individual particles. Now, in the particles, they're heating based on conduction. So as the particle is heated by radiation or from convection, the heat on the surface is conducted inward to raise the temperature of the inner part of the particle. Now, this model is a very fine scale model. I should have put millimeters here instead of centimeters, but you get the idea. These cells that you're seeing at the bottom of the screen, these can be literally millimeters across and larger. But the important thing is that it's able to capture the fuel bed heterogeneity, the structure, these gaps, right? Here's a gap. That gap is just, say, a centimeter wide or a few centimeters wide. You need a fine scale model to capture the effect of the fine scale discontinuities on fire spread. Okay, and that's what produces these thresholds. If we're talking about bunch grasses and we're talking about cheat grass in the variable structure there, you need a fine scale model to capture that if you want the physics to be represented. This model here, because it's a one-dimensional model, just going in a straight line, is extremely fast. On the order of seconds, you can make calculations. So what we want to do is be able to apply a model like this and test it and see how well it represents the effect of different continuity and moisture contents associated with, for example, green strips, right? That's one of the treatments that's being proposed for broad scale application throughout the Great Basin. And we would like to have a model that represents those processes in a physically realistic way, and yet is practical for pretty much anybody to use to understand how these fuel modifications affect fire. And so the experiments that are needed are something like this. So on the left-hand side, what you're seeing, here we have a road, we have roadside conversions of the cheatgrass, invasive cheatgrass, to more of a bunch grass situation, and with discontinuities and increased fuel moisture in the summer part of the season. And then upwind, of course, we have the cheatgrass area. What we would very much need to do and like to do is to be able to run fire from the cheatgrass all the way into the treatment and see how it changes. Just like Gil Dustin did with the landscape level treatments, we'd like to be able to do this for these green strips. Okay, and of course, inside these different types, we would take the necessary measurements to verify how the heat transfer is taking place, how the ignitions are taking place, and how it differs between the different types. So here's an animation, and I'll play this a couple times for you, just give you a flavor of this. This is an animation of the model behavior. And let me stop it right here. So what you're seeing here in the upper part is the flame dimensions. Flame height is a function of distance along the fuel transect. So at about 30 meters, what we've introduced here is a change in the fuel type from a continuous block of fuel here in this upper row to and this is not literally the height. This is just the representation of the two different types, type 1 and type 2. So type 1 is a continuous block, almost identical fuel characteristics to cheatgrass, very continuous. On the bottom row here is the second type in sequence, is a series of discontinuous clumps. And so what we want to be able to do is to simulate how does the process of fire behavior change as it goes from continuous types to the discontinuous. And so what you're seeing here is that the fire is spreading along, it's increasing in intensity, the flames are getting larger, and it hits the discontinuity or the change in the types, and suddenly the flames get shorter and eventually die out. Now, this is not a contrived example, this is a real example. The simulation is showing us what happens here. The other thing I want to point out is look at the colors. The colors are the temperature of the fuel, surface temperature of the fuel. So all the reds here indicate temperatures exceeding the nominal ignition temperature. And then we have oranges and yellows and greens out to blue, indicating the heating region as the fire is approaching. And this heating is coming from radiation, convection, and comes along. And of course, then we start to have gaps. And these gaps delay the forward heat transfer, making the fire slow down and eventually become extinguished. Okay, so in each fuel type, we can measure a whole bunch of things that relate to how particles are heating and igniting. We can measure the convective heat flux, the particle surface temperature, the radiant heat flux, the core temperature, and the gas temperature. Now, uniform cheatgrass on the left, bunch grass on the right. I'm not going to go into a lot of details here, other than to say that, look, in the uniform cheatgrass type, what we're seeing is much longer forward heating distances. The curve there is descending rapidly from the edge of the fire, which is right here at distance 0. That's the edge of the fire. This is ignition right here. And you can see the convective heat flux and the gas temperature and the radiation all reach their peak right when the fire hits. Okay, well then that decays, of course, away from the edge of the fire. Look here in the bunch grasses, because the intensity is much lower and the forward heating from radiation and convection is much lower, the the forward extent that this heat is felt by fuels is much, much less. They're much closer distances, and that's the reason that the fire is spreading slower. So what we need to do is to be able to verify that. This is just another graph showing these different stages of fire spreading along this transect. The spread rate accelerates over distance as the fire goes along, and it finally reaches the maximum. And then the flame length tracks pretty much the same. And then as soon as it hits this 30-meter level, what happens is you end up getting a decrease in both spread rate and intensity to the point where it finally goes out. Last slide is just a schematic of the kind of instrumentation that we would need to measure these different heat fluxes and heating characteristics in the different types. You're seeing a series of radiometers, you're seeing a series of thermocouples extending from one type through the transition to the next type. And this kind of instrumentation, if we could keep the fire front straight, which we can, what we can try to understand is how the radiant flux and the convective heat flux actually change as a function of fuel structure, and how that in turn affects the coupled system of fire spread. So that concludes my talk. Thank you very much.